Hello and welcome to another lecture of classical motion of a single particle. We continue our discussion on the motion under a central force. So, after having discussed various properties of a central force, what in this lecture I will mostly be talking about is some different features related to the dynamics and energetics of the central force, and actually I will be mostly concentrating on the energetics part. So, we have already discussed the dynamics properties, the constants of motions and how you can in a 2D system where we already know that every motion under a central force is effectively 2-dimensional, takes place in a plane. We know that how to decompose the velocity vector, the acceleration vector, and hence the force vector as well in the radial and cross radial component. And as you know that for force or acceleration vector, the cross radial component identically vanishes, then we actually showed that this is totally consistent with the conservation of the angular momentum. Okay. So, here we are again recapitulating what we have done in terms of this kinematics and dynamics, and so after that I will try to say what we will do in this lecture. So, here you can see, if you remember, this is the position vector, and this is true for for in general for any dimensional space. And if you now we have shown that for a central force field, where the force field is basically given by this, the motion takes place effectively in a plane which is the plane perpendicular to the angular momentum direction. And then we said that this is the velocity vector which has two components, the radial and the cross radial component, and we also calculated the acceleration in general in a plane polar coordinate system, and where we already finally claimed that for a central force motion this part identically vanishes and this part is the only surviving part to contribute to the dynamics. Okay. We also discussed about this specific constant of motion r square theta dot, which is equal to h, which is nothing but the magnitude of angular momentum per unit mass. You can see m h is equal to L. So, h is nothing but L by m, and we also said that since angular momentum is a constant vector, it should have a constant direction as well, and this direction will be nothing but the direction which you get just by doing the cross product of r cap and the theta cap, that is the radial direction unit vector and the cross radial direction unit vector. Okay. Now, what we have not yet discussed is the energetics part under a central force motion, and as you will see that this is also very interesting. So, we will first also already somehow discuss that central force is by definition is a conservative force field. So, central force is conservative, that we know, okay, because this is a curl-less field and it can also be written as a gradient of a scalar for all these reasons you know, and that is why its total mechanical energy, which is nothing but the half m v square, v is the speed here actually, okay, v square plus the potential energy is a constant quantity. Now, how to write that explicitly just after knowing all these expressions? So, you can easily write half m. So, this is also equal to v dot v and plus the phi is equal to constant. I can write this constant as E. Okay. I can say that okay, my phi is, so as you know, like sometimes we also have the conventional symbol for phi, which is v. So, for the sake of somehow popularity, I change this symbol to v here, so that people can also relate relate this symbol with the symbols which are appearing in several books and several materials. Okay. So, this is a capital V, of course. Then half m v dot v, and v you know you will have these two components. Okay. So, what will be the v dot v? So, that will simply be, if you do r dot square plus r square theta dot square. Okay. So, remember here r cap and theta cap, these directions are mutually orthogonal. So, the dot product of, just remember, r dot theta, r cap dot theta cap is 0. Okay. So, and also r cap dot r cap is 1, okay, and theta cap dot theta cap is also 1, that you just remember. Okay. Plus V is equal to E. My only point is that here you can see that your kinetic energy, so this is the part of the kinetic energy. Your kinetic energy has two parts, one is this and another is this. Although this is an energy which is a scalar, and you really do not need to say that this is my x component, this is my y component, as we in general do for a vector. Somehow it will be somehow useful if we mentally compartmentalize two part of the kinetic energy. You will see why. So, I can call this is the kinetic energy which is coming from the radial part, and this is the kinetic energy which is coming from the cross radial part. Radial part and cross radial part means radial part of the speed and cross radial part, I mean radial part of the velocity and cross radial part of the velocity. Okay. So, if I now write m r dot square and I use this theta dot is equal to h by r square, I can simply write, which I already have written as well, that h square by r to the 4 times r square. So, r square will be here, and this theta dot square is nothing but h square by r to the 4 plus v is equal to E. And then you can write half m r dot square plus h square by r square plus v is equal to E. Now, you see here I am just writing this whole expression in a slightly different manner. I am writing the expression just like this, half m h square by r square plus v, which I also know for a central force should be a function of r only, because if you remember that v is basically, so I am just going to a little bit behind, so you can have the connection. So, you see that if I write gradient of v minus a gradient of v is f, and f has only this, actually v will simply be integration of f r dr with a minus sign, and which actually gives you that v is also a function of r. Okay. You please just check this thing. Now, if you have this information with you, you can write the whole energy conservation like this. And as I said in the last lecture that I mean a central force, the motion under a central force can always be thought to be effectively one dimension. So, now if you just think this as an effective one dimensional motion, so this actually with that imagination you can think this is the effective kinetic energy and this is the effective potential energy, although you know that one part of the effective potential energy is actually the kinetic energy in practice, okay, and which comes from the cross radial part of the velocity. But you can also think just like this, because you just see that you can say that okay, I will just call the kinetic energy which involves just the dot of my space coordinate, and here the only visible space coordinate is r and not theta. So, you can say that okay, whenever I can see r dot and it is the square of r dot, then I call that as a kinetic energy. Okay. I have no problem, but this is of course not the physical picture, this is just an effective picture. Okay. So, this is the effective, in general we do not call that effective, I am just writing it for your convenience, effective kinetic energy. However, for this part people love to call that the whole thing as effective potential energy. Okay. Now, whenever you write this, you can actually think that okay, now I can write the whole thing as I should not change the color. I can write half m r dot square plus, I will now do something. I will write, instead of h square, I will write L square by m square. Okay? So, I will actually have L square by 2 m r square plus V of r, which I again write like this, is equal to my E, the total energy. Now, you see, you can now write the whole thing as the energy conservation in an effective 1D motion. And if you can write that, you can also draw the energy diagram and you can analyze the motion of the particle in such a diagram. Then you can simply write, it is my r and this is my, I can call this as V effective. This is my V effective. Okay. In the y axis, V effective I will plot, and in the r axis I will plot the displacement. Only the the displacement, when we just consider r to be the sole displacement coordinate or space coordinate. Okay. Yeah. So, you see that here, let us say you will have a curve like that, let us say. Okay. I do not have any problem. Then I am telling you that what will be the motion of the particle if I give the particle energy which will be equal to, let us say this, and another energy which will be equal to, let us say this. Okay. So, E1 and E2. So, now you see we have to be a little more careful. Okay. For example, this is the origin. We said that okay, so whenever this total energy and potential curve they intersect each other, we have the turning point, and the turning point. So, we talked then the motion in a true, in true one dimension, right. Now, there we concluded that whenever the particle reaches the turning point, its kinetic energy vanishes. Here you will see that exactly the same thing here will also happen, that whenever I say that the V effective curve will meet exactly the E1. So, its kinetic energy which looks like this vanishes, but is this its true kinetic energy? We know the answer, no, it is not. So, its effective kinetic energy vanishes. So, you see the point is that here in effective one dimension, turning points are the points where simply, at least in the case of the central force motions, okay, otherwise the discussion has no meaning, of course. So, if you have this effective one dimension motion and you just encounter a turning point over here. So, let us say some turning point is it as at some r is equal to r star. Okay. Then I can say okay, so at that point the effective kinetic energy of the particle is 0. So, its r dot is equal to 0. So, here r dot is equal to 0, but remember this does not say the particle is at rest. So, this does not say. So, the particle is not at rest, because we know that a part of the true kinetic energy belongs to this part, and that is the cross radial part, which the kinetic energy, the part of the kinetic energy which came from the cross radial part of the velocity. And if you now understand that what happens to the velocity of the particle, you will see that the velocity at turning point will have. So, the general formula expression for velocity is this in 2D plane polar, and if this is 0 at turning point, the velocity will simply be given by this. So, actually at turning point in 1D motion here, the particle is not at rest, the particle has a pure tangential or cross radial movement. Okay? The velocity is exactly at the cross radial direction. Okay? So, now you see that you try to understand what is the meaning of that. So, if you have a radial direction, and I am just saying that if this is such a point where you can think that this r, so this is the origin and the particle's position vector here is such an r that at this point the velocity will be exactly directed. I can take another direction, directed to the cross radial direction, then it means that you are just moving in the tangential direction without changing your modulus of r vector, that means the r scalar. Okay? And so, now if you think of a circular orbit, let us say a particle is moving in a circular orbit. So, would it be very strange for you if I say that every point on the trajectory will be a turning point? Okay? And it is actually the truth. Okay? So, I am now going to just do some analysis. So, depending on this, so you see again here just to make a complementary statement over here, whenever the particle will have E2, once again the particle has an energy E2, okay, then again this particle will have, you see, 2 turning points. Now, these 2 turning points will simply say that beyond those the values of r will not be increased or decreased, but the points will, or the particle will actually move in the cross radial direction at those points. So, somehow we agree on that point that whenever irrespectively of the fact that whether the particle is really at rest or not, one thing is true also for effective one dimensional motion here, that whenever it reaches the turning point, so it gives you, for the given energy, it gives you the upper bound and the lower bound, or somehow a bound for the displacement. So, you see with a E2 energy, the particle will have both a lower cutoff and lower bound and an upper bound for the displacement, whereas for this energy E1 it will have a lower bound for the displacement, but upper bound is at infinity. So, again you can see that with respect to this space coordinate r, okay, here the particle will be considered to perform or to exhibit a bounded motion, and here it is showing an unbounded motion. Okay. Now, just to tell you what is the how to calculate those turning points directly. So, we know that at turning point r dot is equal to 0 and E is equal to L square by 2 m r square plus, I should not write phi, I promise to go to v, plus v, which is a function of r. Okay. And this is, again I can call this so this is equal to v effective as well. So, at turning point E will be exactly equal to the effective potential energy. Okay. And then we know that if this is at r star, okay, so basically the turning point is at, so r is equal to some r star. If I assume that, then we also know that L square by 2 m r star square plus v of r star will be equal to E. Okay. So, if I give you, for example, in a problem the value of r for turning point, and you know the constants of motion L, m, E, you can actually find the true potential energy of the particle at that point. Okay. There will be some problems related to that in the assignment as well. Okay. Now, you can also find that if this is in general not a turning point, then what happens? Then we have the formula which looks like this. Okay. And then we can go to, I just choose this blue color, we can go to this, that then we have in general r dot square equal to 2 E minus V by m minus L square by m square r square. This is the general definition, general expression for r dot square, and of course, when the particle is at such an r where it faces a turning point, then r dot square is 0, and this is the total thing is equal to 0, and this part is exactly equal to this part, I mean this part. Yeah. Yeah. Okay. Now, I can also write r dot is equal to plus minus root over 2 E minus V by m by minus h square by r square, or L square by m square r square also works. Okay, if I do not, maybe at this point I do not want to confuse much, already there will be other points where calculations are pretty difficult. Okay. Yeah. So, L square by m square r square. Okay. Now, even if you do not understand what is exactly happening when the particle is changing its displacement from one r to the other, one very common, I mean very straightforward thing you can notice is that this r dot is a variable which changes in a motion continuously. Okay. And it can also have a plus or minus values. So, somehow even if you do not analyze the nature of this total function which is under this root over, and actually you take also you include also the root over the whole function, how really it changes. One thing we can just do using our common sense, that this changes continuously, and whenever it changes continuously and can have both positive and negative values. So, the most I mean intuitive thing which comes to our mind is that, for example, so let us say if this r dot starts from some positive value and then the positive value increases, the intuitive value will be, the intuitive thinking will be that after some point it will actually go to some constant value which is the maximum possible value with this positive sign, and then it will start decreasing, continuously decreases and it touches 0, and then it comes to be negative, and then again it increases in the negative sense, again it touches its lower possible value or the lowest value or the minimum value, and then again it starts to increase. Okay. So, this is the simplest way of thinking. If we somehow adopt this thinking, then the type of trajectory or the type of movement which comes to our mind is as simple as that. And you will see in nature in various cases you will have this type of simple curves where the particle, so I can write the particle like this. So, particle, this is the origin and the particle is actually moving like this, okay. Let us say in this direction, just for example, and I can just now say, okay. So, this is the first point, this is the second point, sorry, yeah, okay. I mean it should all come from this point in principle, okay. This is the third point, and now you see that, okay. So, this is the r vector, of course, r1, r2 like this, and when this particle finally reaches like this position, this position, okay. So, you will see for this trajectory this is the maximum possible position for r vector, r scalar, okay. So, that I can call it r max, and after that its value again decreases, okay, and that means that its value so it is touching its maximum, and then so here it will be, it was positive, and then here it will be negative, okay. And although you see that now r dot can be smaller or bigger with respect to how the values of r's or the modulus of r's are changing. Here also for this point, for this type of trajectory, you can also create another situation. So, this is the origin and a particle also moving like this way, from this to this way, and I can draw some points also over here, 1, 2, 3, 4, 5, 6, like this. I mean, of course, you have to understand they are simply just to I mean just to clarify those things. They are not just the set of discrete points, they are continuous totally, okay. So, I mean they are infinite number of points over here, okay. I am simply taking a finite number of points, okay. And here you can see that I can again draw this. So, this or this and this and this, okay. You see that here again both the position vector and the magnitude changes, but here from here to here it is actually decreasing. So, r dot, scalar r dot actually is decreasing, I mean scalar r dot is actually negative, and then it comes to a minimum value, okay, where it becomes 0, and then again it increases. So, it is having a positive value. So, if I just say that for this part, for this subpart, r dot is actually less than 0, and for this subpart just after this, I mean this is all are exaggerated just to I mean give you a simple picture what is happening, okay. R dot is greater than 0, and here also you can see that, yeah, here in this part. So, r dot is less than 0 and here r dot is greater than 0, okay. Now, you can just also calculate, so analytically, that if I have this information of r dot which is given by r dot which is given by plus minus root 2 e minus v by m minus L square by m square r square, I can also calculate dt, because this is dr dt. So, if I write dr dt is equal to this, then I can take dt on the to the right side, and dr I can I mean combine with this part which comes to the left side. So, I will have dt is equal to dr by this function of r 2 e minus v by m minus L square m square r square. If I now tell you simply that, okay, just I am giving you some initial value of r which is ri and some initial final value of r, rf, actually you can give me the time for the particle to move from this value to this value, okay. So, I can say 0 to t, okay. So, of course, there is a point to make that they are not, so they will give exactly the real, I mean the proper value of time where there is no intersection, okay. So, yeah, no crossing. Now, again just like this, can you also say the theta angle subtended by the particle from going to this ri to rf? This is also possible. For that you just have to use this trick that you know that r square theta dot is equal to constant h, and that is why d theta dt, which is theta dot, is equal to h by r square, and your I would say dt will be r square over h d theta, and then you can actually say that okay, instead of dt I can totally write h r square by h, sorry, r square by h d theta is equal to dr over root 2 e minus v by m minus L square by m square r square. Then actually by doing this you can have h dr by r square 2 minus v m, which makes the integration a little bit maybe complicated, but finally it is also a function of r. So, you can in principle integrate, and just like here you can calculate r I to r f, you can calculate the term within r I and r f, because this is the only variable over here, and you should know everything as a function of r. You can also calculate this theta I to theta f. Okay. That will give you the delta theta. Now, I am coming to a picture where you can see the motion I am just trying to do in a polar diagram. So, where I just think in terms of r and theta. If I am saying that I have a particle which is doing some arbitrary trajectory, which I in general do not know the equation, I mean I do not know the equation for the trajectory, then at least what I can say that okay, this is the origin, I can draw two concentric circles better, two concentric circles, one is r min and another is r max. Then I can actually say that the particle will always have, so the particle can actually move in between. Okay. So, the particle can move in a complicated trajectory or in a simple trajectory, I do not care for instance, but it will always be inside this annular region bounded by r min and r max. That is what the bounded motion is meaning actually. Okay. So, now you see that if let us say the particle is moving, for example, is going from here and then comes like this, I mean just like this, and then again goes like this and comes like this and like this. Okay. So, every time you see that whenever it touches its minimum value or maximum value, basically they are the turning points. So, the particle just makes its cross radial movement and finally gets another, I mean again moves to complete its trajectory. Okay. Now, you see that even after some finite time, you can have always a possibility that maybe the particle is just moving like this and going, but again when it goes like this, it goes to this, for example, and it is not actually getting back to its final, I mean initial position. So, that means although the particle is moving in a bounded region, the particle is not moving in a closed trajectory. On the other hand, if a particle let us say was starting from this and let us say going like this, somehow doing like this and finally does this, then at least one thing I know, that even if I do not know the equation of the trajectory maybe, but at least the particle has a closed trajectory. Okay. Now, you see how to find the closed trajectory using this relation. For a closed trajectory, you have to understand that whenever the closed trajectory is there, then the angle subtended. So, how to measure the angle? Angle is the polar angle. Okay. So, for example, you just take a line of reference and you, for this position you tell this one is theta 1 for example, for this position you say this is the theta 2 position like this. Okay. Now, if the initial and the final positions are the same, they may or may not be at this point, they may be somewhere here as well. I am just if you have a doubt that maybe they should start from here or here and end like this, no, this is not also I mean necessary. One can actually start like this, something like this, and maybe just come to this point, no problem with that. Okay. So, which is an intermediate value of r. But whenever it meets its initial position, you see with respect to, so the initial r and the final r, okay, you see they are the same. So, you actually try to understand that they are the same position. Okay. So, the theta angle subtended by them, either they are 0 or either they are 0 means the particle did not move at all, or a multiple of 2 pi. Why I am saying a multiple of 2 pi and not simple 2 pi? That is also possible, because I can take another ink over here. I am telling you, let us say the particle starts from here and like let us say going like this, and did not touch this time, and after some times, okay, let us say after 2 times roughly traversing this whole ring, the particle finally reaches here. So, you see that with respect to the angle, this is actually now 2 times 2 pi angle. Okay. So, if this delta theta is a multiple of 2 pi, then we know that the particle actually successfully closes the trajectory. Okay. So, this is not a guarantee for every force. There is a beautiful theorem in the central force whose name is Bertrand's theorem, and Bertrand's theorem basically says that, so for a bounded motion, a closed trajectory is possible only when, of course, this is completely coming from your common sense as well, n times delta theta. I am just writing it, just if you just like move, if you just take some delta theta or something like, I do not know, like you can simply say that I have calculated this delta theta n times, okay, for to be a little bit on safe side. So, just after n times of delta theta, this is a multiple of m times 2 pi. Okay. If you can have this, then actually you have delta theta is equal to m by n 2 pi. So, you see that delta theta is some alpha times 2 pi, where alpha is a rational number. Okay. So, I mean why this thing should appear, once again if you remember the whole thing, that I mean I can just say that, okay, for me this one is the total delta theta calculation when it just goes to 1. Okay. And for again I can say that for me again I am calculating the delta theta like this. Okay. And I also do not know, I can actually say that, okay, many a times instead of doing like this, many a times it is actually maybe doing like this. So, that is also sometimes, yeah, like this. Okay. So, whatever be this, you will see that instead of just saying that delta theta is equal to some multiple of 2 pi, we simply say that n times delta theta is equal to m times 2 pi. If you have this relation, then you have a closed trajectory. Okay. And only for two force laws, I would say only for two central force laws, every bounded motion assertively gives, or I mean I should say the correct sentence, assertively associates a closed trajectory. You remember, this is the statement. So, only for two central force laws, every bounded motion is associated with closed trajectory, is always associated with closed trajectory. That is why I said assertively, okay, associates a closed trajectory always. I am just writing this thing for your comprehension. Okay. And this is known as the super famous Bertrand's theorem. And now the question is, which two laws? So, the first one is where f is proportional to 1 over r square and f is proportional to r. I mean, this is just the inverse square law. So, if you now think of the attractive inverse square force law, so this type of laws are actually very common in nature, starting from the planetary motions right to the motions of this Coulomb interactions. Another force law is this one, which you can also easily understand. This is the force law. If you think of an attractive one, so this will be a force law for a simple harmonic oscillator. Okay? And this fact actually compels us in a positive way, of course, compels us to study in more detail about two laws. One is the inverse square force law. So, the inverse square force law and the harmonic force law. Okay. And that is exactly our the topic of our next lectures. Okay. Thank you.